Hello everyone, welcome back to Science Simply, where complex doesn't have to be complicated. You've probably got a revision sheet somewhere with something like this on it. Gradient of a distance time graph equals speed. Gradient of a velocity time graph equals acceleration. Area under a velocity time graph equals displacement. And you read it and you go, okay, I got it. And then you walk into the exam and it's gone. Or if you somehow got it worse, you've got half of it. You remember there's something about a gradient and something about area, but you can't remember which graph it applies to or what quantity it gives you. Here's why that happens. You've been given four separate rules to memorize, and your brain quite reasonably refuses. So here's what we're going to do instead. These are two ideas, just two, that explain every single thing about every single one of these graphs. Once you've got both of them, the four rules just don't fall out. You don't need to memorize them because they'll be very obvious, alright? Let's go. So first, what does slope actually mean? No, not the formula. I mean, what actually is it exactly? Slope tells you how fast the y value is changing compared to the x value. That's it. For every one step you take to the right along the x, how much does y go up or down? The key word is rate. Slope is always a rate of change. So here's an example you already understand, even if you've never thought about it this way. So your phone battery percentage is on the y-axis and time is on the x-axis. So you've definitely looked at the graph in your phone settings and thought, why is it dying so fast? You're already reading the slope. A steep drop means high drain rate. A shallow section means something's barely using any power. A flat line means the phone's off or charging just enough to stay steady, right? So the slope of the graph is your battery drain rate. The units, percentage per hour, percent per hour. That's the change in y or delta y divided by the change in x, delta x. Change in percentage divided by change in time. And here's the thing that makes this useful for physics. Those units, percent per hour, are telling you exactly what the slope represents. Percent per hour is a drain rate. If y were in meters and x were in seconds, delta y by delta x would be meters per second, and that's speed, right? And the unit of the gradient always equals the unit of y divided by the unit of x. And those units tell you exactly what physical quantity you've just calculated before you even check, right? Simple. So here's the formula. Gradient equals delta y by delta x. Steep slope, y is changing fast. Flat line, y is not changing, the slope is 0. Downward slope, y is decreasing, the slope is negative. The sign tells you the direction of change. That's slope. One idea. Now the second one. What area under a graph actually means? So the area under a graph, this one's less obvious. So we're building it up properly now. Back to the earnings analogy. Say you earn £10 an hour. You work in Britain, so you earn £10 an hour. You work for 5 hours. Your total earnings, that's £50. You know that, it's just basic multiplication. Now, put it on a graph, hourly rate on the y-axis, time on the x-axis. The line sits flat at 10. Draw a rectangle from 0 to 5 hours, height of 10. The area, that's 5 times 10, that's 50. And the area is £50. So the area is your earnings. But how do you actually figure that out? Well, look at the units. Pound per hour multiplied by hour. The per hour and the hour cancel out and you're just left with pounds. The units work out automatically. And that's a key insight. Area under a graph gives you y multiplied by x, and the units of that product tell you what the area represents. Well, what happens if your rate changes? Say it's £10 an hour for the first 3 hours, and then drops to £6 an hour for the next two. The graph isn't a flat rectangle anymore. It's a step or slope, depending on how the rate changes, but the principle is identical. You calculate the area of each section separately and add them up. But here's the case you'll need for physics. What if the rate goes negative? You owe money back. The area of that section counts as negative, so you subtract it. So whenever you see an area under the graph in question, you 1. Check the units of y and x, multiply them, that tells you what the area is measuring. 2. Identify the shape, so it can be rectangle, triangle, or trapezium. And 3. Calculate each section while keeping in mind the signs and add them up. Two ideas, let's apply them. The first graph we're going to be talking about in physics is the distance time graph. The y-axis, distance in meters, the x-axis, time in seconds. So the slope, delta distance or change in distance divided by delta t, the change in time. So units, meters per second. And that's speed. So slope equals speed, not because someone told you, but because those are the units and that's what meters per second means. The steep line, the distance is changing fast, it's a high speed. Shallow line or a flat line, the low speed. And the flat line is a distance not changing at all. The object is stationary, so the speed is 0. And also notice that since delta d is 0, why? Because you can see that distance never changes. It's a flat line, which means it doesn't go up, it doesn't go down. The distance covered from the origin is the same. So the speed is 0. One thing worth noting, on a distance time graph, the line actually cannot go downward. Distance only ever increases or stays the same. And that's a useful check in the exam. If your DT graph slopes down, there's something wrong. So let's do a worked example. An object travels from 0 to 60 meters over 10 seconds. The gradient is basically 60 divided by 10 or 6 meters per second. Alright? And the units confirmed it before we even finished it. Meter divided by second equals meters per second, which equals speed. Done. So pause here and let's do this practice problem. Okay, so for the sake of the question, you may not need to do this all the time, but I'm just going to do it. Let's draw the graph. So this is the graph. Ignore the horrible drawing skills. This is D, this is T. Let's draw it. So at T equals 3, so around this point, 3, the object is at 15 meters distance, so 15. Alright, then when it's at 13, so let's draw 13, it's at 75. I'm not keeping in mind the scale, I'm just drawing the graph. So these are the 2 points. Calculate the slope. So slope here, m is the symbol of slope, is y2 minus y1 by x2 minus x1, right? Because change in y, change in x. So what is y2? The second instance of y is 75 meters. And the first instance of y is 15 meters. Minus that. Alright, x2. Let me make the line a bit better. Right. So what is the second instance of x? 13 seconds. What is the first instance of x? 3 seconds. Minus 3 seconds, which equals 60 meters over 10 seconds. Cancel out the zeros. 6 meters per second, and that's the speed. Alright, so don't just write 6, remember write meters per second because that's the unit. Alright, next, speed time graphs. So here y-axis is the speed and x-axis is the time in seconds. So slope is delta speed over delta time. Its unit is meters per second square, and that's acceleration. Slope equals acceleration. Now we haven't covered acceleration yet, but in simple words, acceleration is the rate of change of velocity. Well, in this case it's speed, but it can change based on the context. Here, if the distance is in a straight line, then obviously the velocity will equal to speed. So here, the unit of slope is meters per second square, and that's acceleration. Again, this isn't a rule you're memorizing, it's where you get when you divide meters per second. That's meter per second square, and that's acceleration. The unit just didn't work. And now area means something here, unlike the previous graph. The units of y times unit of x. Meter per second multiplied by second, the seconds cancel, you're left with meters. Meters is the distance, so area under a speed time graph equals distance traveled. It's the same as multiplying speed by time, which is how you normally calculate distance. The graph just lets us do it visually, even when speed isn't constant. Regular shape, just split it into triangles or rectangles. seconds and add the areas. Alright, so here's a worked example. The object accelerates from 0 to 15 meters per second over 5 seconds, then holds at 15 meters per second for 4 more seconds. So slope during the acceleration is 15 divided by 5, which is 3 meters per second square. The triangle area is 37.5 meters. Rectangle area 60. You add them up, total area under the graph gives you 97.5. So let's prove it. So suppose you have an ST graph, speed not displacement, S capital ST. Alright, and then it says from 0 to 15 over 5 seconds. So it looks like this. And then holds at 15 meters per second for 4 more seconds. So 9, and it goes like this. So you can split it into a triangle, and when you multiply 15 into 5 by 2, that's 37.5. And if you do 4, the delta here is 4, multiplied by 15, the height, that's a 60. So ultimately, when you add the areas, you'll get 97.5. Now the displacement time graph looks exactly like a distance time graph. Same axis, same shape of line. The only difference, the y-axis is displacement, not distance. But that one change matters a lot. Slope is still displacement by time, the change in displacement by change in time, and still meters per second. But now it's velocity, not just speed. Because displacement carries direction. A negative gradient doesn't mean you made a mistake. It means the object is moving in the negative direction. So a flat line still means stationary, velocity is 0 obviously. A line going below the x-axis means the object is behind where it started, and the displacement is negative. And that's exactly where marks get dropped. The calculation is identical to the distance time graph, but students see a negative gradient and either panic or ignore the sign. Don't. It's the answer. So here's a real example. The displacement goes from 30 meters, positive 30 meters at t equals 0, to minus 10 at t equals minus 8. So the gradient, you find the change in y, which is minus 10 minus 30, which is equal to minus 40, and the change in x, 8 minus 0, that's just 8, divide those, you get minus 5. So the velocity is minus 5 meters per second, not 5, minus 5. The direction is built into that sign. Alright, so let's do a practice problem. A displacement time graph shows an object at 24 meters when t equals 2 and minus 8 meters when t equals 10. So let's calculate the velocity. So the velocity here, well, let's see. If you divide y by x, you get meter per second. That's the same here as velocity. So to find the slope. So here, m equals y2 minus y1 by x2 minus x1. So what is y2? Second instance, the final displacement is minus 8. Now what's the first instance? Plus 24, but you have to minus it, so minus 24 meters. Second instance of x, that's 10 seconds. T is equal to 2, so minus 2 seconds. So you ultimately get minus 32 meters by 8 seconds, which equals minus, what is it, minus 4 meters per. Now what does the sign of your answer tell you? Well, the sign is negative, right? It's negative, so it's basically the velocity is in the negative direction. Alright, next let's move on to velocity time graph. This is our last graph and it's the most complex of the four, where both slope, area and vectors are used here. So the slope is the change in velocity divided by the change in time, because velocity is on the y-axis and time is on the x-axis. The unit is meters per second square, and that means it's acceleration. So a positive slope means it's positive acceleration, meaning the body is speeding up. If it's negative, if it's slowing down. If it's flat, it's a constant velocity, since the velocity isn't changing, and that means there's zero acceleration. It's the exact same logic as the speed time graph, except now it can go negative. Now the area here is meter per second multiplied by second. So the seconds cancel and the ultimate unit is meters. But here it's displacement, not distance, because velocity has a direction. So the area under the graph still needs to be a vector. If the part of the graph dips below the x-axis, that section represents motion in reverse, and its area counts as negative, so you have to subtract it. Here's what I mean. So there's one case where the negative area from section 2 actually shows up. So let's say a VT graph dips below 0 or below the x-axis. Calculate the area above the x-axis, calculate the area below the x-axis, and subtract the area below from the area above, and that's your net displacement. So here's a worked example for slope. So the velocity increases from 0 to 20 meter per second over 5 seconds. So the gradient here, let's just first draw the graph to explain how this looks. So here is V and here's T. So first over 5 seconds, 5, this is 20. So it goes to here. That's it. That's how it is. And then it holds at 20 seconds, 20 meters per second for 4 more seconds. So this will be 9, and it holds it like this. So the slope acceleration is 20 divided by 5, which is 1 meter per second, right? But the area, if you can divide it into rectangle or triangle, or you can do it in the form of a trapezium, but that's a bit more complicated. Let's keep it simple. So 5 and 20 by 2 is 15, and 4 and 20 is obviously 80. So if you add the areas, you'll get that displacement is 130 meters. Right? Simple. So let's solve the final practice problem here. So a velocity time graph shows an object accelerating from 0 to 12 meters per second over 6 seconds, then decelerating uniformly back to 0 meters per second over the next 2 seconds. So let's calculate the acceleration and the total distance traveled. Now since we're assuming that the object is traveling in a straight line or like in one axis, and it's never negative, so we're going to assume that the displacement is equal to the distance in this case, right? So let's just first draw the graph. It's a velocity time graph, right? So we have to draw the x and y, where this is v, this is t. Well, let's get started. So 0 to 12 over 6 seconds. So 6, 12, and it goes to here. Then decelerating uniformly over the next 3 seconds. So this is 9, this is going to be 9, and it decelerates back to 0. So the velocity should be 0, right, at the x-axis. So it goes down over here, right? So let's calculate the acceleration over the first phase. I'm just going to denote it as a, because a is the symbol of acceleration. We're going to study this quantity in depth in the next video or the next couple of videos. So don't worry if you don't understand what acceleration actually is. Just know you have to calculate the slope of the VT graph. So it's only the first phase, so only this part of the question, right? Only this part of the question. Let's solve it. So the second, so we have to find the slope, right? So use a general slope formula for the distance in the y, difference in the y, difference of the x. All right. So here y2 is 12 meters. Sorry, 12 meters per second. 12 meters per second, right? Because it's velocity, minus 0 meters per second. 0 meters per second. Now, first instance of x is second instance of x is 6 seconds. 6 seconds minus 0 seconds, right? So this becomes 12 by 6. You can divide meters per second by second to get meters per second square. This gives us 2 meters per second square. Now, what is the distance? So you can use I'm just gonna write S because it's displacement. It should give a displacement, but here distance is just equal to this is assumed to be equal to the displacement. So it's the area under the graph. Now you can see this looks like a triangle, right? So we have to use the triangle area formula. So the base here is 9 seconds and the height here is 12 meters per second, and divide that by 2, take cancel. So this becomes, and second also cancel. 6 times 9 is 54. 54 meters is our answer. Alright, simple. Now you can also divide the triangle by 2, but it's actually kind of unnecessary because you can just do the general triangle formula and you base the height by 2. Okay, anything works, but just do something that's the fastest. That's the best possible advice for an exam, right? So here is the summary table for the DT, ST, ST, and VT graphs, right? So two ideas applied 4 times. So slope on the graph is a rate of change of y with respect to x. So units of y divided by unit of x tells you what it is. And remember, slope is basically how much y increases with every single increase of 1 unit towards the x direction. The area under any graph, it's y times x on average. So the units of y tells the unit of x, right? And when you multiply them, that's the unit of the represented physical quantity. So distance time graph, slope equals speed. Speed time graph, slope equals acceleration. Area equals distance. Displacement time graph, slope equals velocity. And velocity time graph, slope equals acceleration, and area equals displacement. And here, and in displacement time graphs and velocity time graphs, the sign matters, right? So you don't need those 4 rows, it's just for the sake of explanation. But what you do need is the two ideas, slope and area. The rows are just what happens when you apply them. Alright? So drop a comment. Did the concepts first approach actually make these click differently? I want to know whether building up slope and area from scratch is more useful than just getting the rules handed to you. If you haven't watched the previous video on distance, displacement, speed, and velocity, that's linked below. And that is the foundation this sets on. Subscribe if this helped. I'll see you in the next one.